Dear students, today we are going to discuss the AASHTO flexible pavement design method. In this method, following factors are considered: pavement performance, traffic, roadbed soils, that is the subgrade material, materials of construction, environment, drainage, and reliability. One by one, we will discuss all these factors. First, look at the pavement performance. There are two types: structural performance and the functional performance. In structural performance, cracking, faulting, raveling, etc. will be considered. Raveling means deterioration of pavement, or you can say the process of making worse. As far as the functional performance is concerned, here the riding comfort is to be considered, and that is measured in terms of roughness of pavement. Serviceability performance is measured in terms of PSI. PSI stands for Present Serviceability Index, which ranges from 0 to 5. When a road is just completed and it is open for the traffic, it will be having the Present Serviceability Index equal to 5. But with passage of time, there will be drop in the value of the Present Serviceability Index. When it reaches 0, it means that road cannot be used now, and that road now will not offer any service to any vehicle. In the design, we consider two Present Serviceability indices: initial Present Serviceability Index P sub I and the terminal Present Serviceability Index P sub T. Normally in the design, we consider initial Present Serviceability Index from 4.2 to 4.5. I will repeat, from 4.2 to 4.5. And terminal Present Serviceability Index is 2.5 to 3 for major highways, 2 for lower class highways, 1.5 for very special cases. A terminal Present Serviceability Index means that your road is having severe problems, but still it can be used. But here the performance is very low. On this particular slide, you can see the scale for the Present Serviceability Index. In fact, this scale was developed during the AASHTO road tests, which were performed from 1956 to 1961 in USA. When the Present Serviceability Index is from 0 to 1, it means your pavement is in very poor condition. From 1 to 2, it is poor, 2 to 3 fair condition, and 3 to 4 good, and 4 to 5 very good. Now here you can see the typical Present Serviceability Index versus time plot. Here you can see in the beginning maximum serviceability index, but with the passage of time it is dropping, and corresponding to this point we have attained that terminal Present Serviceability Index, and this is obviously the loss in the Present Serviceability Index, P naught minus P sub T in this case. Then comes the traffic. In the AASHTO flexible pavement design, traffic is considered in terms of equivalent single axle load for the terminal Present Serviceability Index. For example, you can see the table 20.13 for terminal serviceability index equal to 2.5. We must assume the structural number of the pavement, so we must check if the final structural number is similar to assumed structural number. Higher structural number means stronger pavement. So keep this thing in the mind. I will repeat. Higher structural number means stronger pavement. Thus the impact of traffic on pavement iteration is less. Now when we use SN3 or simply SN, it means structural number of the entire pavement. I will repeat, SN3 or SN. Both symbols are used for the structural number of the entire pavement. Now here you can see the table 20.13a, axial load equivalency factors for flexible pavement single axle corresponding to P sub t equal to 2.5. So corresponding to different axial loads and considering the structural number from 1 to 6, 1, 2, 3, 4, 5, 6. Let's say you are assuming the structural number 5, so obviously this column will be used to pick the equivalency factor. Now this table is for the axial load equivalency factors for flexible pavement tandem axles. Again, terminal serviceability index is 2.5. Roadbed soil. So keep this thing in the mind that whenever we use the term roadbed soil, it means the subgrade. CBR, California bearing ratio, R value, resistance value, and M sub R, resilient modulus, are used to describe the property of the subgrade material. When we discussed the soil works for the pavement, we discussed these important terms, CBR, R value, and the resilient modulus. During the structural design, only M sub R values are used. That means the modulus of resilience will be used. The following conversion formulas are used if either CBR or R values are given. So you can see in this particular formula, you can get the modulus of resilience if the CBR is known to us. And this formula will be used when R value is given. But in these two formulas, you can see that here the CBR is for fine-grained soil which soaks CBR of 10 or less. And here this R value, that means the R is less than or equal to 20. In that case, you can use this formula. The next factor is materials of construction, subbase A3. So keep this thing in the mind that materials of construction, that means for the subbase, we are going to consider this A3. Charts are available to convert the properties of pavement construction material to structural coefficients A3, A2, A1. So keep this in the mind that we are going to consider the three structural coefficients A3, A2, and A1. Now look at that structural coefficient of the subbase, that is A3. And look at this particular figure. Now here you can see the CBR value, R value, the Texas triaxial, and the values are given. Now look at this one, the CBR. Let's say here the CBR value is 22, so corresponding to that you can see the structural coefficient of the subbase is coming equal to 0.10. So in this way we can get A3. Now look at this one, materials of construction, base course, and here we are having the coefficient of the base course, that is A2. Now looking at this particular chart, let's say the CBI value is 100% for the base material, so corresponding to that you can see that this structural coefficient is equal to 0.14. So this A2 is meant for base course material. Now here you can see the materials of construction, asphalt, concrete surface, and here we are using the structural coefficients A1, and for that we can use this particular figure, or you can say the plot. So you can see this one. Let's say the elastic modulus, or you can say the resilient modulus of the asphalt concrete is this much. So corresponding to this, you can see that this value is coming equal to this one in this example 0.44. So this is the structural coefficient for the asphalt concrete material. So this is A1. So I will repeat this, that A1 is the structural coefficient for the asphalt concrete, A2 is for the base course, A3 for subbase. Now here the environment. And temperature and rainfall affect the level of strength of subgrade reflected on the value of resilient modulus. AASHTO developed a chart that helps us to estimate the effective roadbed soil resilient modulus using the serviceability criteria in terms of relative damage U sub F. Determine average U sub F value and obtain M sub R, that is the model of resilience, from the chart or the equation of U sub F. The bar on the right, this is the bar which is present on the right of the table. The bar on the right is used twice. Once to read U sub F value for each month sample modulus of resilience, then to read annual average modulus of resilience using the average UF value. Okay, I will explain this thing. If you are having this data with you, the roadbed soil modulus M sub R for the different months, January, February, March, April, May, June, July, August, September, October, November, December. The values have been accommodated over here. Now one by one, for example, in the January, the average value of the roadbed soil resilient modulus, that is 22,000 pound per square inch. So use this one, this bar. Now in this bar you can see on the left side we are having the resilient modulus, and on the right side we are having the relative damage value. So you can see 22,000 is somewhere here. So you can see this value, the relative damage, that is equal to 0.01. So it has been written over here. So look at that, this scale is 10 raised to power 3 pound per square inch. So where is 22,000? 22,000 is here. So corresponding to that, you can see that the relative damage is 0.01. So in this way, corresponding to these different resilient modulus values, you can get the relative damage. Now just add all the relative damage values. This is 1.59 in this case, and divided by 12. So you are getting the average relative damage value, that is 0.133. Now corresponding to this average relative damage value, this is over here, you can see that the resilient modulus is equal to 7250 in this case pound per square inch. So I will repeat, corresponding to this average relative damage, that is this one, we have got the resilient modulus value, and that is 7250. So this is required, and this is the effective roadbed soil resilient modulus value that we have obtained from this bar. Then comes the drainage. The effect of drainage on the performance of flexible pavement is considered with respect to the effect of water on the strength of the base material and roadbed soil. This effect is expressed by the drainage coefficient m sub I. This value is dependent on the drainage quality and the percent of time. And the percent of time means the time to which a pavement structure is exposed to moisture level approaching saturation. I will repeat, this is very important. Percent of time here, it means the time to which the pavement structure is exposed to moisture level approaching saturation. In this regard, this slide is very useful. Look at this table 20.14. Here we are having the quality of drainage from excellent to very poor. And look at this one, time required to drain the base or sub-base layer to 50% saturation. It is mentioned over here in this column. Now if we take fair quality of drainage, it means 1 week time is required to drain the base or sub-base layer to 50% saturation. Now look at this table, recommended m sub I values, so quality of drainage, and look at the percent of time pavement structure is exposed to moisture level approaching saturation. Less than 1%, 1 to 5%, 5 to 25%, greater than 25%. Obviously, this column is representing the worst scenario. So considering again the fair quality of drainage, corresponding to that, you can see that this drainage factor m sub I is coming equal to 0.8. So you can see that if fair and 30% exposure, then m sub I is equal to 0.8. So look at that, greater than 25%. So this is the worst possibility for the pavement sub-base and the base layer. So in this particular case, you can see that value is coming equal to 0.8. Then comes the reliability. The reliability factor F sub R is computed using the reliability design level R percentage, which determines assurance levels that the pavement section design using the procedure will survive for its design period. Statistically, you can say it is a z-score from the standard normal distribution. The standard deviation S0 that accounts for the chance variation in the traffic forecast and the chance variation in actual pavement performance for a given design period traffic W sub 18. W sub 18 means the equivalent single axle load. Rather you can say accumulated equivalent single axle load. And look at the formula. Log base 10 F sub R, where F sub R is the reliability factor, is equal to minus Z sub R into S naught. And this Z sub R is the standard normal deviation and S naught is the standard deviation. And look at that, reliability and the standard normal deviation. So corresponding to different reliability, you can pick the value S. You can pick the value of Z sub R from this column. And as far as the S node or SD is concerned, for flexible pavement, AASHTO is recommending 0.4 to 0.5 as S node, and for rigid pavement 0.3 to 0.4. So by using the value of S node and Z sub R, we can get F sub R, that is the reliability factor. Functional classification and recommended level of reliability for urban roads and the rural roads. So for interstate and other freeways, principal arterial, collectors and local, AASHTO is recommending these values for the urban roads, and these are for the rural roads for recommended level of reliability. Structural design. The object of the design using The AASHTO method is to determine a flexible pavement structural number adequate to carry the projected design equivalent single axle load. The method discussed in the text applies to equivalent single axle loads greater than 50,000 for the performance period. The design for equivalent single axle loads less than this is usually considered under low volume roads. So look at this equation. This equation can be used to determine the structural number. In fact, so you can see quite complex equation where the structural number of the pavement Sn is equal to this. This is the equation for that structural number. The meaning of the structural number is highlighted over here. How to use figure 20.20 to get structural number based on equation 20.13. Well, this nomograph is available to get the structural number easily without using the equation. So just to facilitate the engineers dealing with the pavement, this nomograph has been developed. Now just recall the different factors that we have discussed over here. Here you can see, I will give you just through one example. I would like to explain the use of this nomograph. Well, this is the reliability. Let's say the reliability is 99. So you are here, and then look at this one. This is the overall standard deviation. Let's say the standard deviation is this one. So starting from here, draw this line like this. This is the turning line. From here you will change the direction of this line. Now if you just look at this one, this is the estimated total equivalent single axle load. So let's say in this case the accumulated equivalent single axle load is this one. So just join this point to this and reach this point B. So simply by using the values of the different parameters we have reached here. Now from this point onward you can see there are three different lines: pink color line, blue color line, and there is a black color line. Well, we need to get the three structural number Sn1, Sn2 and Sn3. Well, you know that Sn3, that is the structural number of the pavement, the total entire pavement. Okay, we were at point B. Now you can see that first, considering the base course, let's say the base course material is having the modulus of resilience 31,000 pound per square inch, and this pink color is meant for the base course. And for the sub-base course, the modulus of resilience is 13,500 pound per square inch. Let's suppose in this example. So blue color. So blue color is meant for this sub-base, you know. And this black color line is for subgrade, where the modulus of resilience is for 9,000 pound per square inch. So first look at this one. Starting from point B and considering the modulus of resilience of the base course material, that is this one, we have drawn this pink colored line. And then look at this one. Here you can see different lines corresponding to design serviceability loss. Let's say the design serviceability loss is this much in this case. So just draw this horizontal line and reach here and then move downward. So in this way you are getting the structural number Sn1, that is equal to 2.6. Now carry out this exercise for the sub-base. And for the sub base, what to do from point B, you will have to draw this blue color line, but you can see that for the sub base material, this modulus of resilience is 13,500 pound per square inch. So that is this one. So just draw this line, blue color line like this, and reach over here. And again, considering the same serviceability laws, move horizontally, and then you can see that SN2 is coming equal to 3.8. And then look at the modulus of resilience of the subgrade, that is 9,000. So that is this one, 9,000. So just draw this black colored line and reach over here, then draw this horizontal line, and considering the same serviceability loss, move downwards and get this SN3, this is 4.4. So you can see that we have got the three structural numbers, SN1, SN2 and SN3. We got SN1 by using the modulus of resilience of base course material. We got SN2 by using the modulus of resilience of subbase. We have got SN3 by using the modulus of resilience of subgrade. Well, I have already explained this thing that SN3 is representing the structural number of the entire pavement, whereas SN2 is representing the structural number of the base course and the surface course. And this SN1, this is representing the structural number of the surface course. To understand this, just consider this thing. Above the base course, you are having asphalt concrete or the surfacing. So this structural number is meant for surfacing. What you are having above the subbase, you are having base course and surfacing. So it means this structural number is meant for base course plus surfacing. And what about the subgrade? Above the subgrade, you are having the total pavement, entire pavement. That means subbase, base and surfacing. So you are getting this structural number, this one. So this is meant for the entire pavement. From this figure, you can get more clear perception. You can see that SN1, this one, SN1, this is SN2, this is SN3. SN3 is meant for the entire pavement. SN2 is meant for the base course plus surfacing. SN1 is meant for surface course only. And to get SN3, what to do? You will have to use the modulus of resilience of the subgrade. To get SN2, you will have to use the modulus of resilience of subbase. To get SN1, you will have to use the modulus of resilience of base course. So simply you can say you will have to use the modulus of resilience of subgrade, subbase and the base course one by one to get SN3, SN2 and SN1 respectively. I have already shown this equation for the structural number Sn, that is meant for the entire pavement. A1 D1 plus A2 D2 M2 plus A3 D3 M3. and SN1 can be written as this one, SN2, and this is the equation for SN3. Use figure 20.15 for A3, figure 20.16 for A2, figure 20.17 for A1, and table 20.14 and 20.15 for M2 and M3. Then find the depth that results in a structural number value close to the structural number value obtained from figure 20.20. So this would be the order. First we will be using this. The structural number that we obtained from the nomograph, we will put that value over here. Along with A1, you can get D1. You can calculate D1. And D1 is the thickness of the surface course. Then just plug in the value of the SN2 that we determined from the nomograph from the previous slide. Put A1 and the D1 that you have determined from this equation over here, along with A2 and M2 value. You could be able to get D2, and this D2 is the thickness of the base course. Then substitute SN3 structural number that you obtained from by using the nomograph on the previous slide. A1 D1, A2 D2 M2 will be substituted along with A3 and M3, and then you can determine D3. D3 is the thickness, this one, that is the thickness of the subbase. So in this way we can get the thicknesses: D1, that is the thickness of surface course, D2 the thickness of the base course, and D3 the thickness of the subbase. Well, look at this table. AASHTO recommended minimum thickness of highway layers. So corresponding to accumulated equivalent single axle load, the minimum thicknesses are recommended for the asphalt concrete and the aggregate base. So you will have to check whether the calculated values are in line of this table or not, because these are the minimum thicknesses. If your calculated values are less than that values, so you will have to use these values which are mentioned, which are recommended in this table. Now here you can see the complete table for the axle load equivalency factor for flexible pavement single axle corresponding to terminal serviceability index 2.5. So this is the complete table. Generally we start from 5, rather you can say 4 to 5, because when you are having the structural number 4 to 5, that means your road is in a good condition. Well, this table, axle load equivalency factor for flexible pavement tandem axles and PT is again 2.5. And this is the complete table where the reliability and the structural normal deviates at sub R, and the other part of the table is present over here. And this is the equivalent axle load factors for single axles considering different terminal serviceability index 2, 2.5 and 3, and these are the structural numbers. And this is the equivalent axle load factors for the tandem axles considering different terminal serviceability index, and this is for the triple axles. And this is the nomograph that we have already discussed is presented over here. So with the help of this nomograph or the design chart, we can determine the structural number SN1, SN2 and SN3. Now at the end of this file you would find one example. If you just look at that, here we are going to design the flexible pavement according to the AASHTO guidelines. Equivalent single axle load are given 1 week for water to be drained. Saturation level moisture exposure is 30% of the time. Asphalt concrete modulus of resilience is given, that is 45 into 10 raised to power 4 pound per square inch. CBR base course 100, CBR the sub base 22, CBR the subgrade, that is 6. So by using the charts, we can determine the modulus of resilience corresponding to the CBR value of 100. The modulus of resilience is 31,000 pound per square inch. For 22 CBR value, the modulus of resilience is 13,500 pound per square inch. So by using the chart that I showed in the beginning, we have got the modulus of resilience. As far as the CBR of the subgrade is concerned, we can use this formula 1500 into CBR to get the modulus of resilience. Why we have got the modulus of resilience? Because the modulus of resilience is needed to get the structural number. We are dealing with the rural interstate, reliability level is 99%, and you know for the flexible pavement is from 80 to 99.9. Standard deviation, that is 0.49, and the range is 0.4 to 0.5. Initial serviceability, that is 4.5, and the terminal serviceability 2.5. If in some numerical these things are not given, so you will have to assume these things yourself. Design M sub I value, that is 0.8 for both sub base and the base. So we consider the fair category in table 20.14, and for greater than 25% category in table 20.15, so we have got 0.8 as M sub I. The design serviceability loss, that is 4.5 minus 2.5, that is 2. This is the initial present serviceability index, this is the terminal, so difference is 2. So this is delta P sub delta PSI. Now here you can see the cross section of the pavement, and you can see that D1, that is the thickness of surfacing, D2 is the thickness of base, and D3 is the thickness of subbase. And keeping this thing in the mind that SN3 is meant for the entire pavement, SN2 is meant for base plus surfacing, SN1 is meant for surfacing. So by using figure 20.20, you can get SN3. So you will have to use the properties of the subgrade, because you can see that what for SN3, which is meant for the entire pavement, the material which is present beneath that, that is subgrade. So for the subgrade, the modulus of resilience 9000 psi. So by using the information given, the question statements and all the data, and by using the nomograph, we have got the SN3 value, that is equal to 4.4. Then SN2. Now here you will have to use the properties of the subbase, and by using the modulus of resilience of the subbase, that is 13,500 pound per square inch, so you will be able to get SN2 from the nomograph, that is 3.8. So SN2, you know, is meant for base plus surfacing, and beneath that you are having the subbase. So that is why we have used the properties of the subbase. Then comes the SN1. Here use properties of the base. So by using the properties of the base, you will be able to get SN1. So modulus of resilience of the base is 31,000 pound per square inch. So SN1 coming from the nomograph, that is 2.6. Now you will have to use these equations. First this one, then this, then this. This would be the order. And here you can see the layer coefficients of different layers. A3, that is 0.1, A2 is 0.14 and A1 is 0.44. In fact, we have got these structural coefficients by using figure 20.15, 20.16 and 20.17. And to get this A3.1, we employed the CBR equal to 22 value for the subbase, and we have got this one. And for A2, we use the CBR equal to 100%, that is for the base, and we have got this value. And here modulus of resilience 45 into 10 raised to power 4 pound per square inch for the asphalt concrete, and we have got this layer coefficient equal to 0.44. Now in this equation, plug in the value SN1, A1 0.44, and D1 is unknown, so D1 is 5.9. So just make it round those 6 inches. So it means D1, that is the thickness of the surfacing, that is 6 inches. If you just plug in this value 6 inches over here along with 0.44, you are getting the structural number 2.64, and that is greater than this one. That's okay. Then use the other equation, this one, and plug in the value 3.8 for SN2, 0.44, and this one, the 6 value that you have got for D1, 0.14, this is D2, and M2, that is for the base material, 0.8. So you are getting this value D1, 10.36. So just you can take in the multiple of 0.5 inch or 10.5 inches on the higher side, you can take it. Now if you just put 10.5 as D2 in this equation along with other parameters, SN2 is coming 3.816, which is greater than this one, so it's okay. Then use the equation number 3 and plug in the SN3 value, A1, D1, A2, D2, N2, A3, D3 is unknown over here, and M3, that is for the subbase material, 0.8, the same value as it M2, just put it that value over here. So in this way you can get D3, that is coming 7.3 inches. You may take it as 7.5 inches. And if you just put 7.5 over here along with all other values, you are getting the structural number equal to 4.416, which is greater than this. So in this way we have got the D1, D2 and D3, and I will repeat that D1, that is the thickness of the surfacing, D2 is the thickness of the base course, and D3 the thickness of the subbase. And a very important point that I have already narrated, that to get SN3 you will have to use the properties of subgrade. To get SN2 you will have to use the properties of the subbase, and to get the SN1 you will have to use the properties of the base material. Thank you.